Okay, so this second problem is a very classic problem. In the absence of any good reason why to be very creative with the control volume, we just pick a simple rectangular control volume. And so for this problem, by default, we'll impose both mass conservation and the momentum equation. Again, the one thing you always have to be careful is to be quite systematic and really check every single side of your control surface and make sure you reason through, is there a volumetric flow rate, yes or no? Is there stress, yes or no? Is it normal, yes? Is it normal or tangential? And when you look at the momentum equation, in which direction do you look at the momentum equation? Do you look at the momentum equation in the x direction or in the y direction? So because this is quite a classic problem, I will go quickly over the solution. So first you write mass conservation, and because we assume steady state, this term here, the left hand side, is equal to 0. And now when you look at the mass flow rate, or since we assume the flow is incompressible, it's essentially the same as the volumetric flow rate coming out of the control surface. We look at all of the sides of the control surface. Now through this size here we have a wall, and therefore we have a no penetration boundary condition, so there is no volumetric flow rate coming out of this surface. We checked out, so we're not going to include this. And the only bits through which we have mass coming in and out are the inlet here and the outlet. So let me give those surfaces a name. This is 1, this is 2, 3, and 4. So through 2 and 1 we have nothing. Through the inlet we have to look at the sign of u. So u, our velocity vector, has component u, and we can assume that the v velocity, well, it doesn't really matter whether it's 0, but the component in the y direction is 0. But our normal vector is pointing this way, so it's the vector -1, 0, and therefore u dot n will be minus u, minus the x component of the velocity field. So this here is then minus u. And then the integral on the outlet, and in the outlet again we have velocity which is u in the x direction, and our normal vector is pointing now in the plus x direction, so this is this will just be u, so rho u ds. Okay, so we have 0 is equal to, now when we look at the control surface 3, we have to make the distinction whether we are at AJ, so at the nozzle, or elsewhere. So elsewhere we'll call the velocity ui, because it's the inlet. So we call the velocity here of the flow which is in train ui at the inlet, and we call u0 the velocity at the outlet. So we're going to have rho times over the surface of the jet we have the velocity u jet, so this is right here, and then plus rho times a minus aj times u inlet. Note that I have a plus here because this minus sign cancels this minus sign, so I have a plus. And then at the outlet I have minus rho times u outlet times a. And this is our mass conservation equation. Our flow is incompressible, so we can rewrite this simply as u0 times a is equal to aj uj plus A minus AJ UI. And note that U0 times A, this is the volumetric flow rate coming out of the pipe. This is exactly what we call Q, the total volumetric flow rate. This here is mass conservation. And now we also write the momentum equation. And because we have a steady state, this term is equal to 0, so the momentum, total momentum inside of a control volume remains equal to 0. We neglect effects of gravity, essentially because we are looking at motion in the x direction, and so we are left with the term which is the flux of momentum minus the flux of the momentum coming out of the control surface, plus the sum or the resultant of all of the forces which apply at the surface. I forgot a ds here. Now this here is our stress vector. The stress vector is equal to, this is from Cauchy, the stress tensor times the normal to the surface. And for a Newtonian fluid, the stress tensor is equal to minus p pressure times the identity matrix plus 2 mu times E, the rate of strain tensor. This here has to do with the viscous stresses. Dot n. Okay, so we always have to look carefully at all of our surfaces, but then again, the momentum equation, because it's a vector equation, it's always useful to think in which direction is it important to impose the momentum equation. And here, clearly the flow, everything is happening in the x direction, and in the y direction there's really not much happening. So it makes sense to right away project the momentum equation onto the x direction and only look at the projection onto the x direction. Now if we do that, then if you write this, then I have 0 equals to minus integral along the control surface of rho. This is a scalar, u dot n is a scalar, u dot n, and I have the vector u left, which I dot on x, so this is u dot n u dot x ds. And actually I'm going to put this on the left hand side. So this now is going to be equal to double integral along the control surface of t, which is my stress vector, dotted on x ds. And we have to look carefully at all of our surfaces. So we'll have those two, this integral, we have to split into, make sure we take into account all of the components on all of the sides of our control surface, and same for the integral of the stress vector. So along surface 1 and 2, which are the side surfaces here, so this surface here 2 and surface 1, we have a no penetration boundary condition, so u dot n is equal to 0. So those terms here don't contribute. Both for 1 and 2, u dot n is equal to 0, so these terms here don't contribute. Now along 3, u dot n is equal to, because the normal vector is pointing to the left, is equal to minus u. So this is integral along 3 of rho times minus u times u dot x, which is u, ds. And here for 4, u dot n is equal to u, so this is rho u squared ds. Now for 3, we also have to make sure we make the distinction between whether we are integrating over the nozzle or whether we're integrating for all of the area outside of the nozzle. So this will result in minus rho times the surface area of the jet, u jet squared, minus rho a minus aj, so all of the rest, times u inlet squared. This is 3, and 4 is just rho times a times the velocity at the outlet squared. So this is for the flux of momentum. And now for the stress tensor, we also have to integrate the stress vector along the 4 surfaces. So let's start at let's start with surface 1, 2, 3, and 4. So when we look at those surfaces, actually what the problem says is essentially that we can neglect the effect of viscosity, right? So even though there is mixing here, it does say that the shear stress at the boundary, or the effect of viscosity, is negligible. So we only have to take into account the effect of pressure. So in this problem here, where did I write it? We can neglect the effect of viscosity. So we only have pressure. Now, let's consider our two side surfaces, 1 and 2. Do we have pressure apply? Of course we do, right? So there is pressure, but remember, pressure always acts in the direction normal to your surface, right? And since we are projecting, so the pressure is here on the bottom surface, we have P in the y direction. But because we are interested only in the momentum balance in the x direction, then this pressure doesn't contribute to net force in the x direction. Okay, so it's important that you always this is why it's important that you project the momentum equation onto a certain axis, because a lot of sometimes the effect of pressure will or will not be relevant. So the pressure in particular acting on 1 and 2, because it's acting in the normal direction, so this is in the y direction here, it does not contribute when we project onto x. Right? It doesn't mean that pressure doesn't that there is no pressure applied. There is, but x dot t is equal to 0 here, because only pressure applies. And then on surface 3, what do we have? Well, on surface 3 we have pressure also, which is acting in the positive direction. So let me call this pressure at the inlet. This is Pi. So here we have Pi times A, and at the outlet we have Pa plus delta P times A. Now Pi we don't know, but we can find, we can express it, and we can find it from Bernoulli. So we know here that the flow is laminar in this region. We know that the flow is at rest in compartment 1. So if we follow a streamline somewhere here, at some point we have a point where the pressure is P0 and the velocity is 0. And then later on here, when we arrive here, we have Pi at velocity ui, so we can write from Bernoulli along a streamline that P0 is equal to Pi plus 1/2 of rho ui squared. Okay, and therefore Pi is equal to P0 minus 1/2 of rho ui squared. And with that, we're essentially done. I don't have time to finish writing it down, but if you computed it, you would get, if you put all the terms together, then you get that delta P is equal to, so you get this expression here. I'll let you do the calculation, and you can further simplify it, and you can do a number of assumptions. You can assume that if you want this pump to be, assuming this pump is actually doing something interesting, in that case that means that the volumetric flow rate Q, the total volumetric flow rate Q, is much larger than the one through the jet. Right? So if you assume this, and if you also assume that the area of the jet is much more than A, then you can further simplify the expression, and you get that. So once you assumed once you made those assumptions that Aj is much more than A and that Q is much more than Aj times Vj, you can further simplify delta P to this, and so then it makes everything a bit easier to plot. And so you see that delta P will be depends on Q. Right, so if you plot delta P as a function of Q, this would be an inverted parabola, which will look roughly like this. Right, so you clearly see that so in the case where delta P is equal to 0, so if you had if you were not pushing against any pressure gradient, then you would maximize the volumetric flow rate, and this maximum volumetric flow rate is equal to, so this is here, when delta P is equal to 0, then the volumetric flow rate is equal to the square root of 2 times Aj times A times Ug squared. And conversely, there is a maximum delta P against which then you can no longer push. So then there is no more volumetric flow rate here, and that the delta P is equal to rho Aj divided by A Vj squared.